This is FRQ number one on the UCM and gravitation packet. It's a circular motion question. They say a box of mass m is held in place by friction and it rides on the flatbed of a truck which is traveling at a constant speed v. The truck is on an unbanked circular roadway having radius of curvature r. On the diagram, indicate and label all forces acting on the box. Well, friction is what's keeping the box on the flatbed, so that's directed radially inward. And that's the only force in that plane. The downward force is just the force of gravity, and there's also an upwards force, and we could label that the normal force. So those are the three forces acting on the box. They ask about what condition must be satisfied by the coefficient of static friction between the box and the truck bed in order to stay on the truck. So they give us some kind of constants they want us to use, some variables. And so we know that the static frictional force, which I'll call F sub FR, the frictional force is equal to the center seeking force or the centripetal force. So this is the condition that must be met. Now I'm just going to make some substitutions. The frictional force is supplied by mu static times the normal force, and the centripetal force is just mv squared over r. So our leftover force, this is Newton's second law, F equals ma, but in circular motion, it's a sub c, which is v squared over r, when multiplied by m gives us this expression. So now I have this stuff. We should recognize that in the y direction that the normal force and the weight are equal in magnitude in opposite direction. I mean, technically we would say then that Fn minus mg is equal to 0. This is in the y direction, by the way. And therefore, Fn is equal to mg, which I can then substitute right here. That's going to be mg. I've substituted in for Fn. That's still mu static. And then I have mv squared over r. We can see that the masses are going to drop out of this, so we don't need to know the mass of this thing. And I can solve this for mu static. It's going to be mu static is equal to v squared over g times r. I'm just writing it as a capital R because that's what they had here. So that's my my expression. And we can say then that that is the minimum value of mu static. That's when it just supplies the value of v. Remember, mu static can be a variable between different numbers, 0 and some maximum value. So as long as mu static is greater than that ratio of v squared over g times r, I'm going to be in good shape and the box isn't going to move. It could also be equal to it and it still wouldn't move as long as it's not less than. And so that would be kind of my best answer for the magnitude of the static coefficient of friction mu static. Okay, now we have this roadway in the kind of next part, and it's banked. The box remains in place. So now we can see that the normal force, which I'll label in the diagram, is directed perpendicular or normal to the truck bed. That makes sense, hence the name. There's also a gravitational force acting downward. That doesn't change, mg. And so, part C asks me to sketch and clearly label the two forces acting on the box under these conditions. There we go. And then they say which, if either of the two forces acting on the box is greater in magnitude. By the way, notice that there's no friction anymore. They told us that the truck bed is frictionless. That's why I didn't sketch it in. And if I wanted to, I could redraw that normal force into its x and y components, which is what I'm going to do here. I'm going to call this Fn. That's the y component, Fny. And that's going to be equal in magnitude, but opposite in direction to the weight, mg. Mg is still acting downward. Now, it's this, once I resolve this thing, we can see that there's an x component, and the x component is what's giving us the center seeking force. That's why the box moves in a circle. So when we kind of sketch it out this way, we can see that the y component of the normal force is equal to the weight, And they're asking us to compare these two forces. So if the y component of the vector is equal to the weight, then the normal force has to be larger than the weight force. So I'm gonna write that out as Fn must be larger than mg. And that's my answer to part D of FRQ number 1 from the UCM gravitation packet.